There we have it. Thank you so much for tuning in our videos. So this will be um, another tutorial for the searching algorithm. So this one here, this will be a jump search. So right now, we'll begin to illustrate what is jump search all about. So when we say jump search, it is a searching algorithm which is designed for a sorted array. Instead of checking each element sequentially as in linear search, it jumps out ahead by fixed steps or block size to quickly narrow down the range where the target might be located. Once the probable block is identified, so in this case right now, a linear search is performed within that block to find the target's exact position. Say, for example, you have a certain array. Then, if you were able to search by three jump consecutive three in each jump, then if you were able to like pass by with the um target, so you have to move back into the previous or move back into the previous element to actually search them. Now, once you go back in there, you will begin to perform the linear search accordingly. In that way, you could be able to find that given element, if and only if the element is located in that place. Now, once the probable block is identified, a linear search is as what I mentioned earlier, is then and efficiently bridges the gap between linear and binary search for sorted arrays, offering better performance rather than linear search and more straightforward implementation than binary search, especially when memory usage is concerned. So this is good because imagine you're looking a name or a name in a phone book. For example, instead of checking every name one by one, you can do jumping to the middle or dividing like binary search. So you can also flip through every pages like for example you have a lot of phone book then but you can definitely jump either 10 pages or 3 pages if you have a lot of phone books sa iyong mga notebook for example. So once you pass the chunk where the name should be, you can backtrack a little bit and go page by page in a smaller range. That's how you will deal with the jump search actually. If you can picture out the scenario that I've given. Now this will be the search steps for the jump search that you have to make sure that your array is sorted. Because jump search only works in sorted arrays. If it's not sorted, don't even bother because it won't work at all. So and afterwards, you have to determine the optimal jump size and the optimal block size. It's somewhat typically step is equals to the square root of n, where n is the number of elements in your array. Now here then there's no exception at all. The jump search will really be suitable or will only work for the um sorted array already. And then it will be less time because as if you can picture out with the details, it will likely avoid you a lot of hassles, for example, in the future. Now initialize the search range. Set previews equals to 0. And since it's the beginning of your current block, and then jump ahead by blocks while the value at array name or step n -1 is less than your target, x move press or step a big step was n, and if previous is beyond array priv greater than equals to n target's not there, or else you have to return a -1. So in this case, by the way, class, if for example, if your array minimum is definitely your target, if For example, if your target is actually you were able to pass by with a target, so you can move back a little bit in the previous exactly the previous jump that you've actually deal earlier. Then afterwards you will do the linear search later, or else if after the linear search then you were not able to find the elements, so you can return -1. So perform linear search in the identified block from previous to mean step and search linearly if array I is equals to X, return the next one. So that's how you will deal with that. You have to return -1. That is -1 if you cannot deal with the searching algorithm. Then return -1 if the element is not found. If the end of the block is reached and the X isn't found, return -1. So in this one here right now, if and only if you were able to find the elements, you can return to a specific element that I mean the specific index. Where is that located? That element, is it located? That is simple actually, and we'll begin to figure out in the latter part in the examples on this another video. Now here I'm so sorry. You will definitely the time complexity and for the average case that is depends on two main factors, the number of jumps and the linear search inside the black. So for jumping through the black size, the jump size is generally chosen to be the square root of this array size, like a square root of n. So that is the implementation of this one. How does it work then? So particularly, the jump size will matter with the spirit event. For example, you're having 11 steps right there, then you could be able to somewhat deal with that already. We're beginning to picture out everything of how this algorithm runs. And the number of jumps in the worst case, you will need to jump across the entire array, stepping by the block size each time since you're jumping by the square root of n. The number of jumps needed is approximately n divided by n, which is still equates to square root of n. So for this one right now, for the average case, depends on two main factor, the same thing. Linear search inside a block, linear search in a block. Once you've identified a block where the element might be, you perform a linear search inside the block. The block size is square root of n, so in this worst case, you might need to check up to the square root of n elements in the block. So it will be still in the square root of n as well in the time complexity for that. And the same with the best case. The best case occurs when the target element is located at one of the block jump position or within the first block. Worst case as well, that is square root of O notation of square root of n plus a square root of n that will still increase as O notation of square root of n. The worst case occurs when you need to jump across the entire array and then search through the last blocks. That's how it works then. Yeah. For the space complexity, that is a time complexity of O of 1, since jump search only requires a small number of extra variables for the current position. Additionally, it does not require any additional memory allocations that grows with the size um, I'm sorry, that goes with the size of the input. So it is an in-place algorithm that operates with a constant space. So anyway, that is the jump search all about, and we'll begin to picture out that in the next video and see you in the